Hi, I'm Wally from BLACKDOT Energy, and part of the Soul Train awareness campaign is visiting various commercial solar thermal installations. We're visiting various sites today with delegates. This particular one is at the University of Pretoria, at the Onderstepoort residences, where the biggest singly connected solar thermal installation in the southern hemisphere has been done by Henning Holm. So let's go meet Henning Holm and see how he's done this significant solar thermal installation.
Ladies and gentlemen, welcome. Although this is not my premises, we did the consulting and the installation of this plant here. This is the Onderstepoort residences as such, so it's not the rest of the campus is just north of us. This installation is, as it stands here, still currently the biggest single glazed collector system. Glazed meaning that the collectors have glass above and are insulated at the back. It all feeds to a single system. The area of the collector is more or less 700 square meters, and the storage of the tanks inside about 40 cubes, so 40,000 liters. So there were some initial buildings built right at the beginning, the old A block. And then as the department extended, they extended the residences as well, because Onderstepoort is a very odd place. There's no conventional residential area very close to this place, and so all the students need to basically live here unless they really travel in and out, and because they can't leave this campus and close it as many others can, they are here to a great extent continuously. So you'll see there are always a few students left. It's a bit like the medicine guys. Well, until recently we thought they can't leave us, but they can apparently. But the idea is that you obviously need to continuously look after the animals on the campus, and that's why it's always active. But it is still in the summer season, which basically starts around now when the exams are finished till 10th or 12th of January. It's virtually empty, which means this whole system needs to be able to handle those type of energy loads while there is no consumption. And the strange thing obviously about it is it's summer holiday, so everyone's gone, but at the same time we've got the best sunshine time here, right? So it's always, so we find that these systems go into stagnation, and what happens then is you get vapor in the system, and and I'll show you some things that we do. For the same reason, you'll find that the panels are relatively steep, so they're orientated more towards the winter months. So that's the one reason, but the other reason is that in winter we consume more water, basically because it takes us longer to wake up, I think. But it's also here in the Highveld dustier, so we do a lot more washing. But we also need more energy because the water is colder. So we start, instead of starting at 20 or 21 degrees heating up to 60, we're starting somewhere at 12 degrees heating up to 60 degrees. So there's a longer path for us to go. And in addition, the electricity tariff for the winter is also higher. And this is purely because of a higher consumption. So the Eskom and the municipalities obviously charge more for that tariff. So it's not about only kilowatt hours or the joules that we need, but the absolute cost of energy during the winter as well that makes this orientation going higher. What was nice about this side is that everything orientates exactly north, so we've got true north looking straight up. And so when we extended this building, campus here, these new blocks were added to the campus, and the idea was to get away. So I'm not the architect on this, there's a different set of architects that worked on this, but the idea was to create a campus that's a bit more urban, it's nice to live. Residences, which we all went straight lines of buildings. So the idea was to create a bit more space. Um, this created in itself a problem that, obviously we needed to link up the different buildings with some pipe work, and so there were long discussions whether this looks architecturally nice or whether this is a disaster, and so because we've got just short of 3 kilometers pipe, in fact, so 2.85 kilometers of circulation pipe going around on the site. And so I'll show you, there's this one big line going here on the circulation, which became a feature to this whole development as well. And at some places you'll see pipes going at high level, you see them there at the top. So if you don't specifically point them out, people don't really see them. So and this was part of the point, saying, well, there are different ways of doing this. And then specifically from the carport to the room, so the plant room is behind. They wanted to do the same overhead thing, but there are big bins coming in and out here. And we said, no, we don't want this, because if they've got the lather or something on the roof, they'll drag it along. So we've got the pipes going underground, which sounds simple, but it's a pretty hard thing to do, specifically if you think 17 tons of trucks are going above this, and you need to do this for even a day, So this piece of piping down here was a bit of a challenge to get this done and clad it. So if someone doesn't get his breaks after a good night party, we obviously don't want our whole hot water system being damaged as well. Okay. What you see on the panels here is they always come in banks. So we've got 4 big arrays. The one is this one, then the 2 that you see left and right of there, and there's a third one on the building just behind that. And then each bank or each array has a few banks, and so they're 1, 2, 3, 4, 5, 6 up here, because the water flows that way and back in a different bank. Okay, and what we're doing is we're putting these panels in series and parallel. So if you put them in parallel, you can have a higher flow because the pipes are actually going parallel. If you put them in series, you have a higher resistance, but at the same time you have a lower flow. And the idea is that I go in with the water at, say, 20 degrees, and I keep on heating it until it's virtually 60 degrees and comes back. So this is what we call a low flow concept. And the idea is that I take the water very slow through the system. I lose a bit of efficiency on the panel because the absolute temperature in the panel is higher, but I gain a lot in the system efficiency. Okay, and so I need to pump less, I've got less resistance, and if I do this, my pipes become substantially smaller. And as you know, copper pipe is extensively expensive, and so we're trying to reduce the copper as much as possible. We've actually got a few tons of copper just on this system here, just to give you an idea of what we're talking about. So as you reduce the pipe, you also reduce the insulation going around it, and so you've got less losses on the system as well. So the system becomes more efficient, even if the
Talking about series now, series connection.
that series connection, yeah. So and so you'll see they are in parallels. We can look at it at the back. It's very difficult to see this, but they 3 in parallel, and those 3 in banks of 3 then are in series, this way and that way. Okay, and so you'll see there's a repetitive, and you can see it on those valves. Those valves are actually balancing valves, right? And then next to it you'll see a thermometer, and the idea is to check whether I've got equal flow through it. Question always is why flat collectors or vacuum tubes. We're working in the range of 60 degrees. That's what we need to achieve by regulation. And so if I look at the cost effectiveness of flat plate collectors against vacuum tubes at that temperature level, and with the radiation that we've got here, in honest to put, this is by far the cheapest way to do it. Okay. So We did for the same organization for Tux at the dining hall, a vacuum tube system, a large vacuum tube system. And there the idea is that we want far higher temperatures because we want to melt fats and wash the starches off the plates. So we're doing about 3,000 meals a day. And that's why we used a vacuum tube system there, because we're running at temperatures of 90 to 105 degrees Celsius. Okay, so it goes into the washing machine straight, very different here. Okay, so from the collectors, we've got very small pumps, then I'll show you. We've got very small pumps, and so because the pumps are running continuously, that becomes also a lot of energy, which one needs to calculate in the whole system, right? And so with this system, we've only got 80 watt and smaller pumps left. Now, just to give you an idea, this plant is about 4 years old. Our first plant we built about, large plant we built about 10 years ago. And that plant is about half the size and has a 7.5 kilowatt motor driving, so 7,500 watts motor driving the water. Whilst here we've got 4 times 80, so 320 watts. Just as a comparison in what is possible in design. I'll show you some plants later which are a lot smaller, but there the pumps get down to about 3 watts. And obviously as this runs long time, so it runs virtually the whole day, that becomes on its own also a lot of energy. And then from that, so we've got these buffer tanks. So we call it a buffer tank if we don't consume the water in that tank. So it's a low pressure tank, and it's got no internal coating because there is no new oxygen coming into it, so it can't rust. Okay, and the big advantage of it is, one, it is safe because there's no pressure, and no pressure valves can go wrong and what have you. And two, is you avoid this whole set of coating inside, which is about a third of the vessel's price. And what does this mean in effect for the system? It means that we don't need to do that certification every month, because if you've got a pressure vessel, you need to certify it every year, and that certification per tank is somewhere around 5,000 to 7,000 rand per vessel. Now, you know, just on the University of Pretoria campus, we did over 35 tanks, just us. And so there are many other companies as well. So you can imagine what this would cost a university if they had to certify all those vessels. The second advantage for the consumer is you can't get in any Legionella. So Legionella grows at lower temperatures, somewhere between 55 or 35 and 55, depending on the time that you leave it at that temperature, right? And so what we've got is this buffer tank, and then we've got a freshwater station. And a freshwater station is just another heat exchanger, which instantaneously heats the cold water with the energy from the buffer tank. So as the cold water flows into the system, it heats up by flowing through this heat exchanger, and you draw the energy out of this buffer tank to heat up that water. So I'll show you inside how that works as well. And then it circulates the water all along these bigger pipes that you see there at the top. And these pipes then take the water to all the different points. In this case, we built, so they are just valves connected. On that side, they were old geysers, so we had a valve, and you took out the geyser and connected it to the system. Some of those pipes in the building itself, they're not insulated, because that's how the building was. And well, I must add to it that the concept there was also different. So everyone's got a hand wash in his room with long pipes going through that whole system, and then central bathroom. Here they did per level a central small bathroom. So all the piping is very compact, and that makes a big difference on energy and the way you consume it. When we designed this here, we helped the architect with all the energy design as well. So from a passive design, so the building as well. So it's properly insulated, the pipes are insulated. You'll see the taps are push taps, so you press it and it runs for, say, a minute or so, and then it stops. Yeah, and so you can press it again. And so they didn't want mixing valves here. So normally we've got this for the shower houses, or we've got mixing valves. but because men and women are different in terms of the temperature they want to shower at, and because this is a mixed hostel or residence, they didn't want that. So we have to have actually 2 mixing valves at each shower, right? So you'll find that ladies need, I don't know, 3 or 4 degrees more in temperature. They sober, you see, they don't need to sober up in the shower. We need it cold. Yes.
It would be the other way around.
Maybe.
Yeah.
No, so we know that, we know 2 interesting facts from measuring on this campus. Not only this campus, but others as well. Ladies shower far hotter than men. And, baths even need more hotter water because it evaporates quickly. But then men consume a lot more water than women. So they're standing longer in the showers. Yep.
That's also that's surprising too.
Sorry, my friend. I knew you're not. Nothing like it. We're doing our washing. In fact, at the other campus, we had a problem that students are, in average, consuming 403 liters of hot water per day per student. Per student per day. 403 liters. And then we found out that the guys were taking their clothes, they're throwing it in the shower, they open the tap, they don't go to class, they come back and they say, my laundry is done. Yes. Yeah. That's the one thing. And the other thing is they literally were standing there sobering up or just waking up, whatever you want to call it. And the third thing was that there was this trick that the guys changed the plugs around. To pull a joke on one another, and so you would early morning turn up the hot water and it would just not come. So sitting in this cold water. And the fourth thing is that the seniors would tell the juniors to go and heat up the bathroom for them. And the way that they heated up the bathrooms, they went down, opened up the hot water tap so that the whole place steamed up. And so that's true for both men and ladies, I should say. So that's apparently a system. So for that same reason, this press tap now. So if you press it, firstly, you can't swap around the colors anymore, right? And you press it and that's gone. So even if you, so in the shower houses at Amplatz, we had this thing that the guys build a clamp. And so they put on the clamp and it goes. If you press this one and you put a clamp on it, it still goes 1 minute and it stops, and so it doesn't work. There's a nasty tap as well which you can press and it goes for a minute, and then it's got a 2-minute recouping time, right? So you need to then wait 2 minutes. But that's bad if you've got soap in your eyes and foam on your head, that doesn't work, so we didn't do it here. So just from this system, so what you see is these 2 buffer tanks, and then you see these outer tank here. And what obviously happens with the buffer tank, as the water heats up, it needs to expand somewhere, right? And it expands into this vessel outside here. And so this is the one cycle. And then the other cycle is the solar loop, and that solar loop obviously is a ring on itself, so they've got a heat exchanger. And that also expands, but it needs in liquid. We've always got expansion, so liquid cannot be compressed, right? That's why liquid in there. So if you hit the brake pedal, that liquid cannot compress and it hits the brake. Okay. Same happens here. So if I've got air in it, air I could compress, but I don't put any air in the system because air would make it rust. Okay. So in the buffer tank, I've just got an expansion pipe which goes into this tank, and this tank normally is about that full. Okay. It's got a little float valve that would, if there's evaporation, it would fill up that again. Then as the temperature goes up, and it can go up from 10 degrees to 95 degrees. Remember, that tank can be far hotter than a normal tank. Yes. The expansion of that material would be up to, what's the maximum? Normal, because it's normal water, right? That expansion can be about 14%. And that 14% I need to cover somehow, and that's what this tank is for. So this water just goes up and up and up. Now as it cools down, it keeps on doing it the whole day, because I'm either heating or cooling by consumption, right? So that water level, if you go and measure it, you'll see it going up and down the whole time. But then I've got the loop that goes between the panels and the heat exchanger to those tanks. That's another closed loop. But that closed loop has got glycol in it because out here I get freezing conditions, right? So that tank would never freeze because it's just too large a space and too hot. But here, those little connectors, they could freeze or what. So I've got about 20% glycol in that system, which means I can take it down to about minus 25, minus 20, somewhere there, right? But now this also expands, and it expands in two ways. Firstly, with temperature. So early morning as the sun comes up, this liquid expands. It's got a different factor because it's not clear water or pure water anymore. It's got a glycol mixture, and so expands less than water does. But then the second expansion, and this is the difficult one, is this December story I told you about. So if the sun is shining, no one consumes, all of a sudden it stops the pump because it doesn't need any more heat in the tank. And what happens then is these panels can get to 150, 160 degrees, and so the water evaporates and it's steam. And obviously one drop of water would all of a sudden fill the whole panels, right? That's the amount of expansion that you get, and that needs to go somewhere else. And that we do with a membrane expansion vessel because water can't move it quick enough. If I would have done it with a system like this, I would probably break a pipe along the way. So these membrane expansion vessels can take up that pressure and go back. So what you're seeing there is we didn't design this structure. This is an engineering job. As you can see, it's well over designed. And so it's got a supply and a return pipe every time. So there are two pipes. So the big one, you can maybe see it on the wall base there. There are two big arrows there. And the supply line is the return line, because on the return line I just want the water to flow. So and the idea is really that if I press that tap, it immediately spits out hot water. And so because water is a resource that is even more scarce in our country than energy. Okay, so the idea is not to waste any water. And by reducing the taps and the shower heads to a flow of about 5 to 6 liters a minute from 25, we don't only reduce the amount of water that we need, but the amount of water that we need to pump, purify, heat, pump again. So it's upstream and downstream, right? So it's not only the municipality, but the whole council that has the benefit of something like this. And this is often the problem, that we're often thinking about our own pocket rather egocentrically, and so but there's a point where if I keep on wasting water, none of us will have it anymore. Fact of the matter is, in South Africa, if I supply the 400 litre per person per day, which the Red Book tells us to do any development, I will have no water tomorrow. So the only reason we're managing that at this point in time is because a lot of people still don't have water. So we cannot work the way we used to work with water. Okay, but it has the added benefit that if I save water, I also save a lot of energy, upstream, downstream, and at my own place of heating and circulating it, obviously. So that whole awareness is very important. Just to give you another example, we did a hot water system in the Free State with Vergeet My Nie, a ladies' residence down there. And to start off, those little sand hours that you get to brush your teeth as a little kid. So they used to be very popular. I don't know, Colgate or one of these guys handed them out by the millions. And so instead of doing anything, we just put those in each shower. And so all these people grew up with these little sand hours, and what they did is, as they got into the shower, they turned it around, and we saved about 15% water just by doing this. So there's a perception, if this thing ran out, I need to be finished, right? So even if they turned it around, it just saved so much by conscious of what you're doing and hurrying yourself up, So you know that when I brushed my teeth years ago, I stopped when this damn thing stopped, because brushing teeth, I guess, is the other way around. You want to make it shorter. But it saved 15% on the water as such, which is tremendous amount of water if you think about it. I think that we had about 220 or 230 ladies in a hostel like this, and there are many of them. What you see behind me are the two buffer tanks. They're also connected in series. So you must imagine, in fact, one tall tank standing one on top of the other. The reason we're doing this is that you can stratify exactly. So I can see you're already showing me how it works. So, and the idea is that very early morning, I can already get some hot water out of the system, even if I've only had very little sunshine. The majority of it is the students' morning and afternoon showering time. So we've got a peak in the morning and a peak in the afternoon. And so you will know from the electricity system there's these peak demands for which I pay a higher tariff. And by storing this into a tank, I don't need to pay for the higher tariff. So the backup elements here, they in fact switched off at about 6 o'clock. Then they don't till late afternoon, evening. So we're avoiding the whole peak time. And why? Because we've got very well insulated storage tank, and I've got my own capacity. So capacity means that I can shift energy demand and energy supply from one another. So that just gives me a bit of leeway in the system. Tanks that you see here, they're insulated with 200 millimeter, so 100 millimeter glass wool and 100 millimeter polyurethane. So if you compare this to the minimum SABS standard of 50 millimeter glass wool, this is obviously far better insulated. And again, the standard of 50 millimeter glass wool is a very old standard, and it's very stupid in fact, but it takes a long time to catch up with these things. If you look at the building standard, it says for this same area 110 millimeter roof insulation, but the difference in temperature in roof is far less than I've got in the tank, so it just doesn't make any sense. So again, SABS standard, or the SAN standard, is a minimum standard. It's definitely not an optimum standard. Okay, so what you'll see here is one of the systems. I'll just explain to it, but there are four of them, right? So this is every time for the solar system. This particular one now is supplying the panels that you see here on the roof. The red big box is a heat exchanger. Okay, so we've just got some plates there, and the idea of a plate heat exchanger is that you've got very little resistance, because the more resistance I've got, the bigger I need to have a pump running. And then you'll see two pumps, a primary pump and a secondary pump. The one is on the solar side, and the other one brings the water from here to the exchanger and back. Okay, so from the bottom of the tank, and then you'll see these three-way valves, and they decide where from the tank do they take and where into the tank do they dump. Okay, so that you just don't take at the bottom and dump at the top, because at some stage the water at the top might be hot, and now if you dilute this with colder water, you're obviously losing something. We differentiate in terms of energy and exergy. So energy, the two have exactly the same amount of joules of energy in here, but exergy is usable energy. So I can heat up all these tanks to, say, 35 degrees. 35 is too cold to consume out there. But if I now take the same 35 and I heat up the top section of the tank to, say, 45, and the rest of it is at 20, I've got the same amount of energy, but I can use that top section. So that's exergy. And the idea is to increase your exergy with the amount of energy that's available. It's a bit technical, but it makes it, you obviously understand it. So this means early morning I can quickly heat up that top of the tank, supply, and I don't need the backup elements to switch on. Okay. So you'll see the pumps are relatively small. These are about 80 watt pumps that you see there. This is a bit smaller system because the two collectors out there are smaller. And then you'll see something different there, which is what we call a strainer, air strainer. So as you fill up the solar system, there's always very small bubbles of air, oxygen in the system. It takes a long while to strain them out. And it's basically just a pipe in a bottle. And as the water comes back, the oxygen bubbles up to the side, and you'll open it. And we do this always manually, because if it's automatic, we never know what's happening. So this way we know exactly what's happening. We come here, we service it. Then there's a controller. This controller can work with a modem to anywhere where you want. You can read off the factors. You can see what's happening. You can see the consumption. You can see your input. You can see that everything, so the idea is that you maintain remotely. Okay, so you don't need to be here all the time to have things looked at. And you can see insulation very thick, so the pipe is always about a third of the whole thickness that you see here. Okay, so and the effectiveness of the insulation depends on the ratio wall thickness to pipe thickness, and that should be 1 to 1 built. So if you see there, you can see the edge insulation pipe, more or less always the same. Everything very well marked, so you know if you come into a plant you can see. And then these vessels that you see above you here are these membrane expansion vessels. They basically are a vessel with a balloon inside, which is pumped up. So, and as the liquid in the solar panel expands, it compresses the air in the balloon. So it gives way and this thing fills with water. And then as it gets colder, it contracts again, and the balloon pushes the water back. And so now I don't need to manage it, it's managing itself. Specifically, if I get a summer system. So it's typically this time of the year, they're doing the maintenance cycle, and you see these two are switched off. So basically the heat that you see there at 60 degrees in the tank comes from only one array at this point in time. Okay, but the consumption of also a lot lower, right? So it's a combination of the two. So unlike Eskom, we do our maintenance then when there's no need for electricity. Okay. So, and then you'll see there's a lot of pipes that are not insulated, and these all feed to the membrane expansion vessel. The reason for that is if I've got water expanding that direction, I actually want to cool it down as quick as possible. So it radiates heat, and they get hellishly hot. In fact, you'll see sometimes they start getting shiny, that funny blue shine to it. That is really steam doing that to it. Okay, so it changes the coloring of the copper, and the copper gets hard by doing this over and over and over again. But you can see all over the pipes going there, and you can see that there's sometimes there are taps in there, so this is that we can maintain blocks independently. So if I need to now maintain that, I'll close down, I'll take out one of them, maintain it, put it back, open it up, so I don't need to redo the whole system. Because to fill a system like that, it's about 4 days. So it's a long process because of the heat, so I need to close it. In fact, if you have this empty and you fill it the first time, it squirts out steam on the other side, so it's a pretty dangerous process if you don't know what you're doing. Okay, but once it's done, it runs. There's no much to it. You'll also see that here some flanges that are not insulated. The idea of this is that we'll expand later to this, at least that was the idea. I don't think it will happen because the new plants, they decided, University of Pretoria has decided to go now with heat pumps. So the system will probably not be expanded as it is. So shall we, what I haven't mentioned is these temperature probes. You'll see a lot of them going into here, different levels at the top there, and they measure temperature at different levels, so you know what's happening in here. You know, it's what's happening out there, some on the panels as well, which you might not see, and then there's some on the circulation pipes, and that way I know exactly which temperatures are where and how I can distribute the energy at best. Okay. So let's go to the other side, and then we'll look at the freshwater stations. Yeah, sorry. So you'll see inside we've got a foil-backed insulation, right? And outside you've got a galvanized sheeting. The reason this is not weather resistant. Okay. In fact, the fact of the matter is you actually don't need to do this inside as well. This is what we actually call a vapor barrier. But we do it because there are guys working here and there's dust and so forth, and this way you can always see, is it properly done? If it's only that rock wool the way you see it here, it might fall off and no one sees it, and so you got these high losses. So that's why we do it like this, so it's just easier to handle. What you see on this side here are the freshwater stations. So at the back you see the cold water coming in. First thing we do is we measure the cold water. So it's a quicker way of measuring because a cold water meter is a lot cheaper than a hot water meter. So if I know I've got cold water flow, that equates to my hot water consumption, right? Thereafter, I've got a strainer with a PRV which handles the pressure, and so then I get this cold water flow of water in here, the big 108 copper pipe here, that little investment going along there. And then it feeds on the one side to the tank. So this feeds the pressure tank. So if there's evaporation in these tanks for the expansion, it will refill that automatically. And then it comes into these heat exchangers. And these freshwater stations are again just a heat exchanger, like on the other side, except that they can handle, they're bigger, because I need to have a huge heat exchange for a very short period of time. In the solar side, I've got a slow heat exchange over a long period of time.